Source PDF link is in the description and in the comment pin, and also there is a video that how to download the source PDF. Today's video we'll be discussing about chemical bonding from physical chemistry. So, types of chemical bonding: ionic bonding, then covalent bonding, metallic bonding. So, for ionic bonding is the electrostatic attraction between oppositely charged ions, that is cations and anions. So, electrostatic attraction between oppositely charged ions, cations and anions. So, electrostatic attraction between oppositely charged ions, For example, this is positively charged ion, sodium ion, and this is negatively charged ion, chloride ion. So sodium chloride forms an ionic bond, that is by electrostatic attraction between cations and anions. So sodium chloride, how can we show the bonding for sodium chloride by dot and cross diagram? So sodium has 11 electron, so 1s2, 2s2, 2p6, 3s1. Chlorine has 17 electron, so 1s2, 2s2, 2p6, 3s2, 3p5. So though for sodium there is 11 electron, so sodium 11 and chlorine 17. So sodium loses an electron to form sodium plus ion, and chlorine gains an electron to form chloride ion. And since sodium loses electron, now the valence shell of sodium does not contain any electron. Since sodium loses the valence electron, that is, it has a valence of 1 electron, so it loses its valence electron. Now it has no valence electron, while chlorine gains the valence electron from sodium to form an octet electronic configuration. So this is the bonding for sodium chloride. Similarly, for calcium chloride, calcium has 2 valence electron, so it gives its 2 valence electron to chlorine, which needs 1 valence electron. So it gives 2 valence electron to 2 chlorine atoms to form 2 chloride ion. So calcium 2 plus ion and 2 chloride ions. So this is the ionic bonding. Then for ionic bonding, so ionic compounds have high melting and boiling point. Due to strong electrostatic forces of attraction. Ionic compounds have high melting and boiling point due to strong electrostatic forces of attraction between oppositely charged ions. Then, ionic compound does not conduct electricity in the solid state. That means, in the solid state, the ions are packed closely together, but it can conduct electricity in the molten state or in aqueous solution. So, ionic compound does not conduct electricity in the solid state, but can conduct electricity in the molten state or in aqueous solution, because in the molten state or in aqueous solution, ions are free to move. That means, now in molten state or in aqueous solution, sodium plus ion and chloride minus ion can move, and this ion enables ionic compound to conduct electricity. Then, ionic compound have giant lattice structure. So, ionic compound have giant lattice structure. Then, most ionic compounds are soluble in water. So, ionic compounds have giant lattice structure. Most ionic compounds are soluble in water. So, ionic compounds have high melting and boiling point, can conduct electricity in the molten or in aqueous solution, but does not conduct electricity in the solid state. Then, ionic compounds have giant lattice structure, and most ionic compounds are soluble in water. For metallic bonding, so metallic bonding, whenever you have asked to show metallic bonding in the question paper, such as in paper 2, so you can draw this diagram, that is positively charged ions and surrounded by delocalized electrons. This shows that the delocalized electrons, so delocalized electrons and positively charged ions or positive ions. So metallic bonding between positive ions and delocalized electron. So metallic bonding is the strong electrostatic forces of attraction between positive metal ions and delocalized electrons. So electrostatic forces of attraction between positive ions and delocalized electrons. So metallic bonding is the strong electrostatic forces of attraction between positive ions and these delocalized electrons. And since there is delocalized electron present, that enables metals to conduct electricity. So as there is delocalized electrons present, so metals can conduct electricity in any state due to free moving electrons. And obviously, metallic compound, since it is a metal, so it has high melting and boiling point, and metallic compounds are usually insoluble in water. Usually means all of metallic compounds are insoluble in water. So For metallic compound, there is strong electrostatic forces of attraction between positive ions and delocalized electrons. Positive ions and delocalized electrons, and metallic compound have high melting and boiling point, can conduct electricity because there is free moving electrons present, and metallic compounds are insoluble in water. Covalent bonding. Covalent bonding is the forces of attraction between the nucleus and shared pair of electrons. So covalent bonding is the forces of attraction between the nucleus and shared pair of electrons. So covalent bonding is the forces of attraction between the nucleus and shared pair of electrons. So shared pair of electrons. Forces of attraction between nucleus and shared pair of electrons. That is the forces of attraction between nucleus and shared pair of electrons. So for ammonia, if we draw the bonding or the structure or dotted cross diagram, so nitrogen has 5 valence electron. So 1, 2, 3, 4 and 5, and each hydrogen shares its 1 electron to form ammonia. For carbon dioxide, so carbon has 4 valence electrons, so 1, 2, 3, 4, and oxygen has 6. 1, 2, 3, 4, 5, 6, 6 to form an octet configuration. So here we can see that there is forces of attraction between the nuclei and shared pair of electrons. So between the nuclei and shared pair of electrons. This is the covalent bonding. Coordinate or dative covalent bond. So coordinate or dative covalent bond. So what is lone pair of electron? Lone pair of electron means that a pair of valence electron that are not involved in bonding. For example, for this compound ammonium, here we can see that these two electrons are not involved in bonding. So not involved in bonding and valence electron. So this is the valence electron and this is the pair of valence electron. So pair of valence electron that is not involved in bonding. So lone pair of electrons means that the pair of electrons that are not involved in bonding. So dative covalent bond, dative or coordinate bond. So what is dative or coordinate bond? So the sharing of a pair of electrons between two atoms where both the electrons in the bond come from the same atom. So it is the sharing of a pair of electrons between two atoms. This is same for covalent compound, sharing of a pair of electrons between two atoms. But the two electrons in the bond come from the same atom. So two electrons in the bond come from the same atom. For example, it has two lone pair of electron, so it uses its lone pair of electron to form dative covalent bond. That is sharing of a pair of electrons between two atoms, sharing of a pair of electrons between two atoms where both the electrons come from the same atom. Both the electrons come from the same atom. Dative covalent bond. For dative bond, you need to remember that one compound has electron deficiency. For example, one compound has electron deficiency. For example, if we refer this as hydrogen, then hydrogen plus ion has no electron. Hydrogen plus ion has no electron, so it has electron deficiency, and the other compound has lone pair of electron. So ammonia has lone pair of electron. That is, you can see that the lone pair of electrons, that nitrogen has 2 electrons. That is a pair of electrons that are not involved in bonding, and these are the valence electron. So pair of valence electron that are not involved in bonding, and hydrogen has no electron. So no electron, that is electron deficiency, and lone pair of electron or the electrons that are not involved in bonding, or the pair of valence electron that are not involved in bonding. So ammonium reacts with hydrogen ion to form ammonium plus ion. So ammonium plus ion, and here we can see that the dative covalent bond. So this is the dative covalent bond, that sharing of a pair of electrons between two atoms where both the electrons in the bond come from the same atom. That is, both the electrons come from nitrogen to form this dative covalent bond. So usually we show the dative covalent bond like this, where this arrow refers to the dative bond and it moves from the atom that gives the lone pair of electron to one that gains the electrons. That is, since nitrogen has lone pair of electron, so the arrow is from nitrogen to another compound. Since it has lone pair of electron, so the arrow is from nitrogen to another compound. Let's suppose this is hydrogen. So this is the ammonium diagram that I have explained. So nitrogen has lone pair of electron that are not involved in bonding. So it bonds with hydrogen. So where both the electrons in the bond come from nitrogen, so it is a dative covalent bond. So dative bond or dative covalent bond or coordinate bond, and the dative bond is shown by this arrow, that is from the lone pair and to another atom which has no electron. So the arrow is from the lone pair. The arrow is from the lone pair. Then for this structure, here aluminum chloride has covalent bond. Then this aluminum chloride has covalent bond. Now these two aluminum chloride are joined together by dative covalent bond or coordinate bond. And for coordinate bond, we need to have an atom that has electron deficiency and the other atom that has lone pair of electron. So chlorine has lone pair of electron, aluminum has electron deficiency. So here aluminum chloride forms a bond where both the electrons in the bond come from chlorine. So it is a dative covalent bond. Again, this aluminum has electron deficiency and this chlorine has lone pair of electron. So again dative covalent bond is formed. And the bond for this dative covalent bond, here we can see that the arrows are from the lone pair. That is from chlorine to aluminum and from chlorine to this aluminum. So that's how we show the dative covalent. Electronegativity. Electronegativity is the power of an atom to attract the shared pair of electron towards itself. So electronegativity is the power of an atom. Power of an atom to attract the shared pair of electron towards itself. For example, two atoms are forming a covalent bond, then the atom that is more electronegative would attract the shared pair of electron towards itself. So electronegativity is the power of an atom to attract the shared pair of electron towards itself. And electronegativity increases across the period and increases up the group. So as we go across the period, electronegativity increases, and as we go up the group, electronegativity increases. Then the factors that influence the electronegativity of element. So nuclear charge. Atoms in the same period with a greater nuclear charge, that means more number of protons, are more likely to attract the bonding pair of electrons. So atoms in the same period with the more nuclear charge or more protons would attract the bonding pair of electron towards itself. So that means suppose atoms are in the same period. Suppose two atoms are in the same period. Now one with more number of protons. So more protons means more positive charge. And since more positive charge, so obviously positive charge would attract the negative charge. So more protons means more positive charge. And so more positive charge means it would attract the more electrons or the more bonding pair of electron towards itself. So more protons means more positive charge or nuclear charge. And since more nuclear charge, so it would obviously attract the more bonding pair of electrons towards itself. Then for atomic radius, atoms in the same group in which the outer electrons are further from the nucleus are less likely to attract the bonding pair of electron because the pull of the positive nucleus on the electron pair is lower. So basically, atoms that are in the same group, now atoms are in the same group, but electrons that are further from the nucleus. So let's suppose two atoms. So if we consider the atoms in the same group, then the electrons that are further from the nucleus, suppose bromine and fluorine. So since for bromine has a larger nucleus, larger nucleus, or we can say that the electron shell is further from the nucleus. So for bromine, the valence electron is further from the nucleus. So since it has the valence electron further from the nucleus, so there is less nuclear attraction on the valence electron or on the bonding pair of electron. So less attraction on the bonding pair of electron compared to fluorine, where the bonding pair of electron are closer to the nucleus. Since for chlorine, the bonding pair of electron is closer to the nucleus, so it would be more electronegative. So electronegative, since electronegativity is the power of an atom to attract the bonding pair of electrons towards itself. So electronegativity is the power of an atom to attract the bonding pair of electron towards itself. So here we can see that obviously fluorine would attract more bonding pair of electron towards itself compared to bromine, because bromine has a larger atomic radius or its bonding pair of electron is further from the nucleus. That means atoms in the same group in which the outer electrons are further from the nucleus. So atoms in the same group with with bonding pair of electrons that are further from the nucleus are less likely to attract the bonding electrons. So less likely to attract the bonding electrons because the pull of the positive nucleus on the electron pair is lower. So the pull of the positive nucleus on the electron pair is lower than compared to an atom that has bonding pair of electron closer to the nucleus. That's why as atomic radius increases, so as atomic radius increases, so less attraction on the bonding pair of electrons. Less attraction means that it is less electronegative, because electronegativity is the power of an atom to attract the shared pair of electron or the bonding pair of electron towards itself. Then for shielding, so nuclear charge, atomic radius and shielding. As shielding, the greater number of inertial electrons, so the greater number of inner electron shells shielding, the lower the effective nuclear charge on the bonding pair of electrons. So shielding means that, so shielding is basically caused by the inertial electrons. That means here we can see that shielding is caused by the inertial electrons. Suppose this is the bonding electron or the bonding electron, and this is the inertial electron. Now this inertial electron causes shielding, and so due to this shielding, there is less nuclear attraction on the bonding pair of electron. Due to this shielding, there is less nuclear attraction on the bonding pair of electron than compared to the atom that has no shielding. So as the shielding increases, so less nuclear attraction on the bonding pair of electron, and so electronegativity decreases. Since electronegativity is the power of an atom to attract the shared pair of electron towards itself. So as the shielding increases, so more inertial electrons, shielding means more inertial electrons, and as the more inertial electrons increases, so less attraction between the nucleus and the bonding pair of electrons. So the factors that influence electronegativity is the nuclear charge, atomic radius, and shielding. As the nuclear charge increases, number of protons increases, so attraction increases. Then atomic radius, as the atomic radius increases, attraction decreases, so electronegativity decreases. Similarly for shielding, as the shielding increases, attraction decreases, so electronegativity also decreases. Polarity in molecules. When the electronegativity values of two atoms forming a covalent bond are same, the pair of electron is equally shared. So we know that electronegativity is the power of an atom to attract the bonding pair of electron towards itself. But if let's suppose both have the same electronegativity, so since they have the same electronegativity, so the electronegativity values cancel each other out, and we can say that the pair of electron is equally shared. So equally shared, or we can say that the molecule is non-polar. And electronegativity is the power of an atom to attract the shared pair of electron towards itself. So to attract the shared pair of electron towards itself. And electronegativity increases across the period and increases up the group. So for HCl, we can see that chlorine is more electronegative compared to hydrogen. So chlorine is more electronegative. But for hydrogen and hydrogen, that is H2, we can see that both have the same electronegativity, so the values cancel each other out. Then for chlorine, both have the same electronegativity, so the values cancel each other out. Then when the electronegativity values of two atoms forming a covalent bond are different, the pair of electron is not equally shared or polar. So as we can see that the electronegativity values between two atoms are not the same. So we refer this as delta negative and delta positive to ensure that it is a charge. So delta positive charge and delta negative charge, or we can say that it is a polarity. Now for electronegativity, so when the electronegativity values of two atoms forming a covalent bond are different, so we can see that this is a polar. That means it is more electronegative and hydrogen is less electronegative. So the pair of electron is not equally shared, so the molecule is polar. So it is more electronegative, it is less electronegative. So the pair of electron is not equally shared. So we can say that this molecule is polar. That is, it has delta positive charge and delta negative charge. Then for ammonia we know that nitrogen is delta negative while hydrogen is delta positive. So this molecule is polar. Then CCl4. Now for CCl4, carbon is delta positive and chlorine all are delta negative. So we can see that The negative charge top and bottom cancel, and left and right cancel. So we can see that the molecule becomes non-polar. That is, the values cancel. So up value cancels with the down value, right cancels with the left value. So ultimately this molecule is non-polar. Molecular forces. So the forces of attraction between one molecule and the neighboring molecule. So intermolecular force is the forces of attraction between one molecule and the neighboring molecule. Intermolecular forces is the forces of attraction between one molecule and the neighboring molecule. Then there are two types of intermolecular forces: permanent dipole forces, or PD, and temporal dipole, or induced dipole, instantaneous dipole, induced dipole. So temporary dipole or instantaneous dipole, induced dipole. So temporary dipole or instantaneous dipole, induced dipole, that is ID force, and permanent dipole force. Now, permanent dipole force is the attraction between two polar molecules. So attraction between two polar molecules is the permanent dipole force. For example, here hydrogen is delta positive, chlorine is delta negative. Hydrogen is delta positive, chlorine is delta negative. Now the attraction between two polar molecules, for example, delta negative chlorine from this HCl attracts with the hydrogen, that is HCl from this HCl. So it is the permanent dipole force. And what is temporary dipole? The attraction between the electron and the nuclei due to uneven distribution of electrons. So the attraction between the electron and the nuclei due to uneven distribution of electron. So attraction between the electron and the nuclei due to uneven distribution of electron. So what causes this uneven distribution of electron? For example, here we can see that there is uneven distribution of electron. For example, the two electrons from this side move to this side. So this has temporal dipole. So this molecule causes temporal dipole forces or instantaneous dipole induced dipole forces with the another molecule. For example, here we can see that the three molecules, and there is delta. We can see that the electrons move to this side, and so as electrons move to this side becomes positive charge. And due to this electron movement, again electron causes repulsion, or due to this side electrons move to this side. And so here we can see that this side becomes positive charge. Then again electron added positive charge and repel the electrons. So now the electrons move to this side. So here we can see that the temporal dipole or instantaneous dipole induced dipole forces increases with number of electrons. So there is instantaneous dipole induced dipole force between these molecules. So as we can see that there is instantaneous dipole induced dipole forces between the molecules, and it increases with the more number of electrons. That means if there is more number of electrons, then there is more instantaneous dipole induced dipole forces. Instantaneous dipole induced dipole force is the weaker than permanent dipole force. So permanent dipole force is the strongest force then compared to temporal dipole or instantaneous dipole induced dipole intermolecular forces. Hydrogen bonding. So hydrogen bonding is the strongest intermolecular forces. So among the intermolecular forces, that is permanent dipole and temporal dipole, hydrogen bonding is the strongest intermolecular force. So hydrogen bonding is the strongest intermolecular force, and hydrogen bonding is caused by hydrogen of one molecule and the lone pair of electron of another molecule. So hydrogen and the lone pair of electron. So hydrogen bond in water, for example, hydrogen bond in water, here we can see that for water, that is H2O. So oxygen has a total of 6 valence electron. So 1, 2, 3, 4, 5, 6. That means here we can see that oxygen has 2 lone pair of electrons. And we know that lone pair of electrons are the pair of electrons that are not involved in bonding. So oxygen has 2 lone pair of electrons. Now hydrogen bonding is caused by lone pair of electron and hydrogen. So lone pair of electron of oxygen and hydrogen is the hydrogen bonding. Then lone pair of electron of oxygen and the hydrogen is the hydrogen bonding. And we know that hydrogen is delta positive charge while oxygen is delta negative charge. So delta positive hydrogen, oxygen delta negative, and hydrogen is delta positive. And this is the hydrogen bonding in water. So this is the hydrogen bonding in water, and so these are the dot lines from the lone pair and to the hydrogen. So this is the hydrogen bond, that is the bonding between hydrogen and the lone pair of electrons for water. Also, that how many hydrogen bonds can one water molecule can form. So here we can see that oxygen has two lone pair, so one hydrogen bond and two hydrogen bond. Then again, these hydrogens can also form hydrogen bond with the lone pair of electrons. So we can see that one water molecule can form four hydrogen bonds. So two bond by the lone pairs and two bond by the hydrogen. That is two bond by the hydrogen is four hydrogen bonds that water molecule can form. Now we will discuss the shape of molecules by whisper theory. So hydrogen, for hydrogen, here we can see that the structure is linear and the bond angle is 180 degree. So the bond angle is 180 degree. Then for boron trifluoride, so boron trifluoride, three fluorines are in three sides, so it is trigonal planar and the bond angle is 120 degree. So it is trigonal planar and the bond angle is 120 degree. Then for CH4, that is methane, so the structure is tetrahedral. So tetrahedral arrangement, and for CH4 usually we draw this like this. So draw the structure like this, that two hydrogens and one hydrogen coming towards you and one hydrogen is moving away from you. So this is the tetrahedral arrangement and the bond angle is 109.5 degree. So tetrahedral arrangement and the bond angle is 109.5 degree. Then for phosphorus pentachloride, it is trigonal bipyramidal. So the structure is trigonal bipyramidal. And the bond angle is 90 degree and 120 degree. Bond angle is 90 degree and 120 degree. Then for trigonal pyramidal. So for trigonal pyramidal, so for ammonia, that is NH3. We know that nitrogen has one lone pair of electron. So instead of forming a trigonal planar structure like this, it forms a trigonal pyramidal with a bond angle of 107 degree instead of 120 degree. This is due to the lone pair of electron, and due to this lone pair of electron, it causes repulsion, and the lone pair of electron causes the greatest repulsion, and due to this greatest repulsion, the bond angle decreases to 107 degree. So this is the structure of ammonia. And for water is bent V-shape or non-linear. So bent V-shape or non-linear. And here is the structure of water. So water, usually we should get water like this, but instead of forming the structure like this, it has two lone pair of electron, and due to this two lone pair of electron, it causes repulsion, and due to this repulsion, the bond angle decreases to 104.5 degree. So bond angle decreases to 104.5 degree. And last of all, sulfur hexafluoride. So for sulfur hexafluoride, here we can see the sulfur and the fluorines. So the structure, we refer this as octahedral, and the bond angles all are 90 degree. So water, linear. So for hydrogen, it is linear. And the bond angle is 180 degree. Then for boron trifluoride, so trigonal pyramidal and the bond angle is 120 degree. CH4, so for CH4, the bond angle is 109.5 degree and it is tetrahedral. Then for phosphorus pentachloride, trigonal bipyramidal, 90 and 120 degree. Then for ammonia, it is 107 degree, and due to this lone pair of electron, the bond angle decreases. Instead of forming a closed triangle, it forms 107 degree bond angle due to this repulsion by the lone pair of electron. Similarly for water, instead of forming a straight line with a bond angle of 180 degree, it forms non-linear or bent or V-shaped structure. So due to this lone pair of electrons that causes repulsion, and the bond angle for water is much less than compared to ammonia, that is 104.5 degree. And for sulfur hexafluoride, octahedral, and the bond angle is 90 degree. And also, these are the bond angle values that I have shown you. That boron trifluoride trigonal planar 120, carbon dioxide linear 180 degrees. So carbon dioxide, carbon and 2 oxygen. So the bond angle is 180 degree without any lone pair for carbon. So since carbon has no lone pair, so the bond angle is 180 degree and it is linear. Then CH4 tetrahedral 109.5. So tetrahedral 109.5. Then for ammonia pyramidal 107, ammonia pyramidal 107. Then for water nonlinear V, so 104.5. So water 104.5. Then sulfur hexafluoride octahedral 90 degree, sulfur hexafluoride octahedral 90 degree. And last of all, phosphorus pentafluoride. So phosphorus pentafluoride or pentachloride. And trigonal bipyramidal 120 at 90 degree, 90 degree and 120 degree. So you need to remember these values. Now sigma bond and pi bond. So covalent bond can be formed when atomic orbitals overlap. So covalent bond can be formed when atomic orbitals overlap. So sigma bond and pi bond. So first of all, here we know that s orbital is circle while p orbital is like this structure. So 2s orbital overlap to form this structure, and 1s, so 1s orbital, atomic orbital in hydrogen overlap to form the covalent bond. So covalent bonds are formed when atomic orbitals overlap. Covalent bonds are formed when atomic orbitals overlap. So we can see that the two atomic orbitals overlap, and so covalent bonds are formed. Covalent bonds are formed when two atomic orbitals overlap. So two s orbital overlap to form this final structure, and so covalent bond can be formed when two atomic orbitals overlap. This is for s orbital. Now, so first of all, what is hybridization? So hybridization is the mixing of atomic orbital. So the mixing of atomic orbital is called hybridization. So hybridization is the mixing of atomic orbital. For example, this atomic orbital mixes with this atomic orbital to form this structure. So hybridization occurs. That is, hybridization is the mixing of atomic orbitals. So hybridization is the mixing of atomic orbitals, and as atomic orbitals overlap, covalent bonds are formed. Hybridization is the mixing of atomic orbitals, and as atomic orbitals overlap, covalent bonds are formed. So mixing S with 3 to 1p type orbitals form sp3, sp2 and sp hybridized orbitals. So mixing S with 3p orbitals form sp3, S with 2p orbital form sp2, S with 1p form sp hybridized orbital. And what is hybridization? Hybridization is mixing of atomic orbital. That is, when two atomic orbitals are mixed, hybridization occurs. So here we can see that p atomic orbital from carbon. So p atomic orbital overlap with s atomic orbital, and so p orbital with s orbital form this structure that we have given like this. So p atomic orbital overlap with s atomic orbital from hydrogen to form this atomic orbital or this molecular orbital. So p atomic orbital overlap with s atomic orbital to form this atomic orbital, and this is sigma bond. So why we call this as sigma bond instead of pi bond? Sigma and pi bond. So instead of pi bond, we call this as sigma bond because sigma bonds are head-on overlap. So what is head-on overlap? We will discuss this. But p orbital overlap with s orbital to form this orbital. Then when two p orbitals overlap, if we just overlap this 2p orbital, then the final molecular orbital is this orbital. So this is also sigma bond. So sigma bonds are the head-on overlap. This is this head and this head overlap to form sigma bond. So sigma bonds are head-on overlap. So or linear end-on overlap. So linear overlap or end-on overlap by sigma bonds. So p with s from this structure and p with p from this molecular orbital. Now p orbital can also overlap by sideways. So this p orbital overlap with this p orbital by sideways to form this p orbital, or so this p orbital, or we can draw this as these are the two centers and this is the structure. So we can draw this either this way or this way. both are the same. So 2p orbitals overlap to form this molecular orbital. Either this or this, both would be correct. And these are called pi bond. Now, what is pi bond and what is sigma bond? Sigma bond. So sigma bonds are head-on overlap. So we can see that both are end-on overlap or head-on overlap. So they overlap by head-on overlap to form sigma bonds. But pi bond is a side overlap. So sideways overlap. So sideways overlap, they form pi bond. That is this side with this side and this side with this side to form pi bond. So you need to remember that sigma bond is a head-on overlap while pi bond is a sideways overlap. So pi bond is the sideways overlap, that is this side with this side and this side with this side. But head-on overlap is from this side to this side. Now, for this structure, that is, you need to remember that the first bond is always sigma bond and the second, third, fourth, fifth, all bonds are pi bond. So this is the first bond, this is the first bond, this is first bond, this is first bond, this is first, this is first bond. So they are all sigma bond. But if let's suppose there is two bond between carbon, then one is sigma, one is pi. If let's suppose another bond, then one is sigma and two bonds are pi bond. If let's suppose 3, 4, 5, 6, 7, 8. So first bond is always sigma bond and the other bonds are always pi bond. So for ethane, so this is ethane. This is not ethane, this is ethene. So ethene. So for ethene, the first bond, so these are all sigma bonds. Then the first bond is a sigma bond. There is sigma. So this is sigma. And the second bond is a pi bond. So first bond is sigma bond and the second bond is pi bond. So p overlap. So p orbital overlap. So the overlap is shown by this diagram. So you can show this in this way or just the two orbitals overlap like this way. Both are the same. So either this way or this way, that is like this, both are the same. So pi bond. Now discussing some questions. So identify the hybridization of carbon atoms in this bond in an alkene. So what is the hybridization of carbon atom? So if we just draw this alkene clearly, then carbon forms 4 bond. So 2 with this carbon and the other 2. So here we can see that what would be the hybridization. So for hybridization, we know that hybridization is calculated by the number of atoms attached plus the number of lone pairs. So number of atoms attached plus the number of lone pairs. So for this carbon, this is attached to 1, 2 and 3 atoms. So this is, the bond is 2, but it is attached to 3 atoms. That is, this is an atom, this is an atom and this is an atom. So now it is attached to 3 atom. So 3 atom, and how many lone pair do carbon have? Carbon have 0 lone pair because it uses all its lone pair to form bond. So 0 lone pair. So it is, since the number is 3, so it is sp2 hybridized. That s is 1 and 2p. So in total there is 3. If let's suppose the answer we get as 4, then it would be sp3 hybridized. So sp3 hybridized, if let's suppose we get a value of 3, then sp2 hybridized. If let's suppose we get a value of 2, then sp hybridized. Now since we get a value, that is, it is attached to 1, 2 and 3 atoms. So number of atoms attached is 3. Therefore it is sp2 hybridized. Draw a label diagram to show in terms of orbital overlap how sigma and pi bonds are made in carbon-carbon double bond. So in this carbon-carbon double bond, we know that there is one sigma bond and the other is pi bond. So for sigma bonds are head-on overlap. So sigma bonds are head-on overlap. So two p orbitals from carbon overlap head-on to form sigma bonds. Similarly for pi bond, two p orbitals overlap by sideways to form pi bond. We can show the pi bond like this or like this. Both would be correct. And this is sigma bond. Sigma bond is the head-on overlap and pi bond is the sideways overlap. Now the number of carbon atoms, that is sp2 and sp3 hybridized. So if we draw the structure, then this would be CH3, CH2, then CH2, CH2, then CH2, so CH3, CH2, CH2, then CH2, then again CH2, that is CH2, then CH, CH double bond, then again CH, so CH 1 2 3 and CH3. So now for this structure, so for this carbon, here we can see that this carbon is attached to 3 hydrogen and one other atom. So hybridization is calculated by the number of atoms attached plus the number of lone pairs. So for this carbon, it is attached to 3 hydrogen and one with this carbon. So it is attached to 4 atoms. So 4 atoms, it is attached to 4 atoms. That means it is sp3 hybridized. So this is sp3 hybridized. Then this carbon is attached to one this carbon, then hydrogen, and one to this carbon. So for this carbon, so we can see that it is attached to 4 hydrogen, 4 atoms. So since it is attached to 4 atoms and it has no lone pair, so it is sp3. So it has 4 atoms that are attached. So sp3 hybridized. Similarly, this is also the same structure. So sp3 hybridized. This is also sp3 hybridized. This is, again, if we just draw for this carbon, then this is attached to 2 hydrogen and 1 2 3 4. So it is attached to 4 atoms, 4 different atoms or 4 atoms, and it has no lone pair. So again it is sp3 hybridized. And this carbon, for this carbon, now for this carbon, so for this carbon, this is a bond, then there is hydrogen attached and this double bond, that is CH. Okay, so now we draw this structure like this. So now we can say that this carbon is attached to hydrogen and this atom and this carbon. So what is the number of atoms attached? Atoms attached is 1 2, that is 1 2 and 3. And so though there is double bond, but this double bond is attached to only one atom. So number of atoms attached is 1 2 and 3. So 3 atoms are attached and this carbon has no lone pair. So no lone pair, that means it is sp2 hybridized. sp2 hybridized. So sp2 hybridized. Then for this carbon is, so for this carbon, that is this carbon is attached to 1 and 2 atom, and though there is a double bond, but it is attached to one atom. So double bond, but it is attached to one atom. Therefore this is also 3, that is attached to 3 atoms and no lone pair. So it is also sp2 hybridized. And this carbon is attached to 4 different atoms or 4 atoms. So it is sp3 hybridized. So if it is attached to 4 atoms, sp3 hybridized, 3 atoms, sp2 hybridized, 2 atoms, sp hybridized. So in total there is 6 sp3 and 2 sp2 hybridized and no sp hybridized. And if we just determine what is sp hybridized, then here we can see that there is a triple bond and carbon atom is attached to one other atom. Let's say this carbon. So it is attached to one atom and then the second atom. So 2 atoms are attached and it is attached to 2 atoms, and though there is a triple bond, but it is attached to 2 atoms. So since it is attached to 2 atoms, so it is sp hybridized. So this is sp hybridized. And hybridization is calculated by the number of atoms attached plus the number of lone pairs. Since it has no lone pair, so only the number of atoms attached. But if let's suppose for ammonia, that is NH3, so this is attached to 1 2 3 atoms and one lone pair. So 3 atoms and one lone pair, that is it is 4. So 4 means sp3 hybridized. So 4 means sp3 hybridized. Then for water, we can see that hybridization is calculated by the number of atoms attached plus the number of lone pairs. So oxygen is attached to 2 atoms, that is 1 2. So 2 atom, and what is the number of lone pair? Number of lone pair is 1 2. So 2 lone pair. So the hybridization is 4, that is sp3 hybridized. So the hybridization for this oxygen is sp3 hybridized. There is number of atoms attached plus number of lone pairs.